Hey guys, this is Mrs. Mendy, and today I'm going to talk to you about states of matter and thermal energy and how they're related. And I know you've talked about states of matter before, but you definitely are going to learn something different about that um, that you will have to know for this class. Remember that matter is anything that has mass and takes up space. Different states of matter have different properties that define them, things that we observe about them. All right, now the background of how we're going to understand this is there's kinetic theory of how matter acts. And remember, in science, theory is not just like, oh, simple hypothesis. Theory is a set of interconnected hypotheses that have had lots and lots and lots of support over time. So, theory is pretty much as close as we get to truth in science. Okay, so we really think this is true. Um, or at least we have assumptions that we make that under those assumptions that is true. Okay, so first, all matter is made of tiny particles. Okay, yeah, that makes sense. Atoms and molecules. Particles are in constant motion. Now, this is a little bit weird. It is absolutely true, but it's funny to think. So, like the table that may be in front of you, the floor that is under you, things that feel really still on the molecular level, they are scrabbling around and wiggling like mad. Okay, that is just true, and it is strange. Anyway, so three particles collide with each other; they smack into each other and their container. However, solids don't move enough to collide. They're wiggling, but they're wiggling more slowly so that they're not smacking into each other so much. Four, particles don't lose energy from collisions. Now, this is not true of matter on the human scale. Like if you take a ball and drop it on the floor, it's going to bounce lower and lower and lower and lower because it's losing energy with every collision it has with the floor. Okay, it's losing it as heat energy every single time. That's why it doesn't just keep bouncing at the same height forever. That and a little friction with the air. But that's a collision too. Okay, so let's try this. This is a little interactive and it's linked in Canvas to show you if you wanted to see this. Um, and let's just see how this works. So this will show you how kind of a cartoon of how particles look when they're in the different states of matter. Okay, so here is solid. I'll just click this to make sure that this is lit up so you get that. And you see how these particles are wiggling around, but their relative orientation to each other stays the same. Okay? So they're wiggling around, but they're still staying stuck together. Okay? Now if we do liquid, you can see they're still kind of sticking together, but um they can kind of move past each other. They're mostly moving around, and I'm gonna cool this down a little bit because some of them are escaping and being a gas up here, which happens. There's evaporation. I'm gonna cool that down. Now you can see some of it's getting a little solid. So I'll move that back to liquid again. Okay, now compare this to gas, where the particles are flying around every which way and completely filling the container. Okay, they are completely filling the container in a way that the liquid does not. The liquid only fills a container if, there's no space above there. It fills it all the way up to the tippy top. But if there's space underneath there, the liquid will, because of gravity, stick to the bottom. Now, if it's a solid, it doesn't follow the sides of the container either. Okay. And these may all be uh, properties that you are familiar with. Okay. But you see, as I heat these, so I'm going to heat this up, put some fire. Okay, you can see that the molecules become looser And so these ones down here are liquid. I've heated some of them up so much that they become gas. If I continue heating it up, I can make it all gas. Okay, see? So the difference between these things is not anything about the particles except that it's the energy in each particle, okay? And it is how the particles are relating to each other. Okay, so see, they're bouncing around and they keep bouncing around forever because they don't run out of energy when they smack into anything. Okay, let's go back to here. Okay, so some of the properties of uh, molecules are in a of the states of matter. The molecules in the states of matter. When it's a solid, the atoms are locked together. They stick together. They don't move their relative orientation, which was what I mean is they may be wiggling around, like if back here in the states of matter, they may be wiggling around as a liquid like that, or as a solid, they're wiggling around, but they stay like this one stays next to this one, stays next to this one. Okay, I'm gonna actually show you like, oh, here it is when it's water. So see the water molecules are different. And actually, while I'm in here, I'm gonna show you a neat thing. So see how big this is and how there are big spaces between the water. Now this is ice. This is solid water. But if I put it to be a liquid, look, it's much more dense. And that's just because water molecules have a charge on either end. And so the positives are kind of going next to the negatives, and you get this structure. And the gas is the same. I mean, it's the same as uh, if it were just atoms, like in argon. Okay, but you can see them spinning around. All right. So locked together, so they're not moving relative to the position of each other. In a liquid, the atoms are touching but loose. And I put this here, so water, they always show water for liquid. Sure, that's like the liquid that we know about. But any, any, any matter can be liquid. Okay, any material can be liquid. All right, so here's some iron being poured into a mold made of sand. So anything can be liquid. Bromine, whose atomic uh, symbol is Br, and mercury, Hg, are the only liquid elements at room temperature. Okay, so there are plenty of liquids, but for the elements, these are the only two that are liquid at room temperature. This is very pretty, but dangerous. They sometimes call it quicksilver because it's quick, it looks alive, and of course it's silvery. All right, in a liquid, the particles are touching, but they're loose. They can slide past each other. So notice that liquids are not necessarily more spread out than solids. And I like to say this because lots of elementary textbooks say that they are, but it's not always true. It's kind of mostly true, but not always true. That's not the definition of a liquid or of a solid, is that they're, more dense than a liquid. They're not. And how I know this is because ice floats. Ice floats. Um, okay. All matter can be changed into all the states of matter, no matter what it is, no matter how you think of it as being a gas. It can be a solid, so like air can be a solid. Okay, for gas. In gas, the loose particles are not touching, they are flying everywhere and filling up whatever container there is. If there's not a container, they may be constrained by gravity or other things, but they spread out as much as they can. They fill up the available space. Here are some gases, helium and xenon being put into glass tubes that electricity is run through, kind of like neon lights, but you can also have helium lights or xenon lights. And these colors are slightly different for each element. Okay, so think about the states of matter in this picture. Well, okay, so there's obviously liquid in this water underneath. There's solid in this big chunk of ice. There's gas in that there's certainly water molecules and other gases up here in the air. There's some liquid water in this cloud here, little tiny droplets spread out to be sure, but still counts as liquid. Clouds do. Plasma. Now, this is one that they often don't talk about when you think about states of matter in lower grades. So I'm not sure if that you will know this or not, but you will have probably seen examples of plasma. So like this is a plasma ball, and it is basically a gas with loose electrons. So it has so much energy that the electrons just start popping off and just become this sort of electron soup around the particles. Okay, here's a diagram of what that looks like on the molecular scale. So if this is a gas, if this is a gas, um, and you can see they're different uh, atoms just sort of floating around. They're loose, they're not touching, okay? But they have their electrons on them. This looks like hydrogen because there's only one electron. So in a plasma, there's so much energy, they pop off and they just kind of swim around like this. So here, this electron is not connected to any particular one of these atoms. Okay, so that's a plasma. An example of plasma that is really pretty is the Northern Lights. And I have a video of this linked in Canvas in case you want to see it. Um, but I can't do it in this video because YouTube does not let me do that. Okay, so particles have two competing forces. Their attraction, which makes them want to stick together, and then their kinetic energy that makes them zoom away from each other. Okay, and this attraction is because of electrostatic forces, because they have little charges, and even if they're not charged, they may be partially charged on one side um, momentarily as the electrons are moving around. Okay, so if there's low energy, they can stick together. But if there's higher energy, they overcome that. Okay, they can pull off from each other. Okay, so here is a bizarre thing to think about is that temperature is really a measure of speed. And really, this is really true. Okay, temperature is a measure of speed. It's how fast the particles are going. That's what temperature actually is. Okay, so if you add heat to particles, adding heat gives the particles more kinetic energy. It makes them move faster. Removing heat takes kinetic energy away from particles, so they have a lower kinetic energy. So, if there's not enough kinetic energy to overpower the attraction between them, the particles will stick together. Okay? That attractive force is always there, but how strong it is relative to the kinetic, so like how much it affects the behavior of the particles, depends on how much kinetic energy they have. If they have lots of kinetic energy, they go flying around everywhere and are gases or plasmas. But as they cool down, this is why the particles in liquids and solids will stick together, okay? Because those attractive forces that are smaller, much smaller, but they will become important when the kinetic energy is low. So that's why this is kinetic theory of how this works. It's because it's the kinetic energy of the particles that makes them be in one state of matter or another. Okay, now here is a way of quantifying what is happening when you move from one state of matter to another by adding heat. Okay, so this is a heating graph. Um, and you can see here there is temperature on this axis, the y-axis, and then the amount of heat added I'm sorry, did I say x-axis? This is the y-axis, duh. Okay, temperature on the y-axis, heat added on the x-axis. So as you're heating something up, heat, 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 like that, then the temperature goes up, which you may say like, well, sure, you add heat, the temperature goes up. But that is not always true. It's not always true, which is weird to think, but that's true. So if you're heating up, so here you have, we're talking about, this is for water. So we have solid water over here, ice. But you're heating it up, heating it up, heating it up, heating it up, heating up. And then at this point, something weird happens. It's like you're adding heat, but nothing happens. The temperature does not go up. So what is going on there? Okay, so sometimes you can add heat. So like between here and here, you're adding heat. The heat adding is going up, but the temperature is not going up. And that is because the heat is overpowering the attractive forces between the particles to go to the next highest state. So it doesn't add to the kinetic energy of the, well, I guess that's the temperature of the material, because that heat is being used to break apart the attractive forces. Okay. So right now over here, you have 0 degree stuff that is solid and 0 degree stuff over here that is liquid. And it's just getting ready to go into the liquid state. And then when it's all the way liquid, then it will start heating up as you add heat. And then over here, this happens in the transition between liquid to gas, because gas is over here, liquid is here. Here you have to add a lot to go from, and this is funny. Okay, so it's not adding temperature. So at this point, you've got 100 degree Celsius, 100 degree water, but it is not a gas yet. So it's at the boiling point. It's at the temperature where it becomes gas, but you have to add in all this energy, all this heat between here and here, here and here, to get it from liquid to gas. Okay? It's a lot. It's not inconsiderable. So that's kind of a strange thing that happens. Okay, so why I'm telling you this? Why, it's standard. Okay, you have to know how to read this heating curve. I know it's straight lines, but they still call it a graph like this is just a curve, whether it's a straight line curve or not. Okay, on the x-axis, it can be time spent heating or the heat added. Those are pretty much going to be the same thing. So sometimes it depends on what you're actually measuring when you make this graph. And then temperature is up here. Okay? So what do you have to know about this? Okay? You have to know what is happening in each one of these sections of the heating curve. I gave you an example for water, but let's just say what is happening generally. Okay, generally, this part down here, it's going to have a non-zero slope. It's going to have a slope going up. That's when it's a solid. Okay? These flat places, these are the transitions between states. Okay, whoops, wrong way. Okay, so in this little green bit here, this is where the solid is changing to a liquid. Okay, you may think like, oh, it's going up in temperature, it's melting. No, it's not. It's not. It's totally solid right here until it starts to melt right here. Okay, then this part is liquid, and when you add more heat, the temperature goes up. But then you get to here, and this is where the liquid changes to a gas. Okay, so it goes over here, you're changing this to a gas. And remember, this can happen to anything. This can be iron changing to a gas. It can be glass changing to a gas. Anything, anything, anything can be a gas. Okay, and then up here, when it starts going up again, that's when it's actually a gas. Okay, you will absolutely be asked to diagram a graph like this. So please draw this, pay attention, label the parts. Okay, so looking at this is a heating curve for iron. So seeing like, do you get what I just said? Where does iron become a liquid? Okay, where iron becomes a liquid is right here, the flat parts. The flat parts. So it's at the right temperature where it could become a liquid here, but it does not become a liquid until it gets to here. Okay, so this part right here, this flat part, is where iron is transitioning to become a liquid. Where does iron become a gas? Well, it's this flat part here. Holy cow, look at how much energy you have to put into iron to change it from liquid to gas. A lot. A lot, a lot. And can iron be a gas? Sure. There's iron in the sun. That iron is probably plasma, actually. Okay? Heating curve. That's it for today, and I will see you next time.